Well, 13.8 billion years ago, the universe as we know it began from an explosion. Actually, a cosmic explosion from a singular point in space called the singularity, which at the time was the point where all the universe's mass and energy was compressed into a tiny, infinitesimal point. That explosion was nicknamed the Big Bang. But again, this is just a theory and not completely proven. Questions like, from where did the matter and energy which formed the singularity come from? Since at the time there was only nothingness. What if I could tell you something totally different, the answer to it all? Did you know we can't and might never be able to observe the entirety of the universe? The observable universe, ever heard of it? The observable universe refers to the part of the universe that we can potentially see from Earth using telescopes and other astronomical instruments. It's the portion of the cosmos from which light and other forms of radiation have had enough time to reach us since the beginning of the universe. And at the end of the observable universe, there's a boundary beyond which light hasn't had enough time to reach us yet. But also, no matter how we travel, even at the speed of light, in order to reach that boundary, we can never reach it. You'd know there's something there, but can't get to it. Because the closer you get to it, the farther it expands away from you. And there's one thing that fits this scenario. That's inside the event horizon of a black hole. Some scientists have begun to entertain the idea that our entire universe might actually exist inside a black hole. Well, let's delve into the facts and flaws about this theory. Well, if we are going to check out the universe inside a black hole theory, we've got to start at the beginning of it all, the Big Bang theory. It suggests that about 13.8 billion years ago, the universe began as an incredibly hot, dense state and has been expanding and cooling ever since. The universe started from an extremely compact and dense point called a singularity. Then it rapidly expanded in a process known as cosmic inflation, enlarging within a fraction of a second. Meanwhile, as the universe was expanding, fundamental particles like protons, neutrons, and electrons were formed. Simple elements such as hydrogen and helium were created within a few minutes after the Big Bang. Around 380,000 years after the event, the universe cooled enough for electrons to combine with nuclei, forming neutral atoms. This allowed light to travel freely, resulting in the cosmic microwave background radiation, a faint glow detectable throughout the universe. Over millions of years, gravity caused matter to group together, forming stars, galaxies, and larger structures, eventually leading to the complex universe we see today. The Big Bang theory is supported by various evidence, including cosmic microwave background radiation, the abundance of light elements, and observations indicating an expanding universe. Nonetheless, there are still unknowns, such as the nature of cosmic inflation, dark matter, and dark energy, which scientists are researching to refine our understanding of the universe's history. But you'd probably be wondering about how the Big Bang theory came about. Well, let's find out, shall we? Early cosmological speculations date back to ancient times when civilizations pondered the nature of the cosmos. Ancient Greek philosophers such as Aristotle and Plato contemplated the existence of a prime mover or a first cause that set the universe into motion. Talked about that in my first video. However, these early ideas lack the empirical evidence necessary to support or develop a comprehensive theory. But take a look at this. In the early 20th century, the astronomer Edwin Hubble made a groundbreaking observation. He discovered that galaxies were moving away from each other and that the more distant galaxies were receding at greater speeds. This observation provided strong evidence for an expanding universe. An expanding universe? As in when the universe was expanding just after the Big Bang happened? Yes, the universe still expands even till now. Also, in 1927, the Belgian physicist and Catholic priest Georges Lemaitre proposed a hypothesis that the universe originated from an extremely hot and dense state in the past, which he referred to as the primeval atom. Lemaitre's idea was based on solving Einstein's equations and explaining the observed expansion of the universe. And most ultimately, in 1965, Arno Penzias and Robert Wilson accidentally discovered a faint background radiation pervading the universe. This radiation, known as the cosmic microwave background CMB, was found to be uniformly distributed and had properties consistent with a hot, early phase of the universe. And yes, it is the same radiation to the one we discussed earlier in the video. The CMB became a crucial piece of evidence supporting the Big Bang theory. Well, now that we've known about the theory, let's hear its critics. Ideas that dare to challenge the brilliance of the Big Bang. The horizon problem, ever heard of it? The horizon problem refers to the challenge of explaining the uniformity of temperature and other properties observed across the large-scale structure of the universe. Critics argue that the Big Bang theory struggles to account for how regions of the universe that were not in causal contact have the same temperature and exhibit similar characteristics. Well, if we take a good look at that point, you would agree that something doesn't quite add up. Let's take a look at dark matter and dark energy. The Big Bang theory relies on the presence of dark matter and dark energy to explain certain observational phenomena such as the rotation curves of galaxies and the accelerated expansion of the universe, respectively. Critics question the existence and nature of these hypothetical components and propose alternative explanations or modifications to existing theories. And let's not forget about critics around the infamous singularity. The singularity has been criticized for being an area where our current understanding of physics breaks down. Some critics argue that our understanding of the early universe may require a more comprehensive theory that combines general relativity and quantum mechanics. Well, I am not completely dismissing the Big Bang theory as untrue. Yes, sure, its contributions to our comprehension of the universe are noteworthy, and its predictions harmonize with diverse observations. Nevertheless, it is crucial to acknowledge the gaps and unanswered queries that persist within the theory. Let's talk about black holes. Well, black holes are born from the dramatic collapse of massive stars. When these stellar giants exhaust their nuclear fuel, their cores implode under the crushing force of gravity, creating a gravitational singularity, a point of infinite density and unfathomable power. One of the defining features of black holes is their event horizon. It is a boundary beyond which nothing can escape their gravitational clutches. Crossing the event horizon is a one-way journey into the cosmic unknown, where even light cannot outrun the gravitational pull. Venturing into an event horizon is like dancing on the edge of oblivion. Time slows to a crawl, and space warps and bends like a cosmic roller coaster. The intense gravitational pull stretches and distorts everything in its path, distorting the very fabric of reality. It's as if you've stumbled into a gravitational whirlpool from which escape seems impossible. Black holes are voracious cosmic predators, capable of consuming matter and energy in their vicinity. As matter spirals into a black hole, it forms an accretion disk, a swirling maelstrom of superheated gases and dust. The extreme conditions within this disk generate intense radiation and jets of matter that shoot out into space, visible to us as cosmic fireworks. Interesting fact, black holes aren't exactly holes. They're a region in space where the gravitational pull is so intense that light cannot escape. That's why it looks like a round void of nothingness. To add to that, these black holes are invisible. And you might be wondering, how in the world can you locate or study them if you can't see them? Well, this might help. Although black holes themselves are invisible, their presence is often revealed through their interactions with surrounding matter and the effects they have on their cosmic neighborhoods. By observing the motion of nearby stars or detecting the X-rays emitted from accretion disks, scientists can indirectly study and measure the properties of black holes. And at the heart of most galaxies lies a supermassive black hole, millions or even billions of times more massive than our Sun. These cosmic giants play a crucial role in galaxy formation and evolution, shaping the structure and dynamics of their galactic hosts. But the mystery deepens. At the heart of a black hole lies the singularity, a mind-bending concept where all known laws of physics crumble. Infinite density and unimaginable forces reside within this cosmic abyss, shrouded in a veil of uncertainty. What lies beyond the singularity? Well, unless we travel inside, we'll never know. You can watch my video on what happens inside a black hole if you wish to find out. Now let's talk about that black hole theory. But before we begin, quick question. Do you buy the idea that our entire universe exists in a black hole? Let me know your answer in the comments. Okay, back to stuff. Imagine, if you will, that the cosmos we observe, with its galaxies, stars, and planets, is but a minute speck within the unfathomable depths of a cosmic singularity. Our universe, once thought to be an expansive canvas stretching infinitely, is now proposed to be encapsulated within the confines of an event horizon, an invisible threshold that separates our reality from the unknown. This reality is referred to as the observable universe. Let me do a recap on the meaning of this observable universe. The observable universe refers to the portion of the universe that we can potentially observe from our vantage point on Earth. It encompasses all matter, galaxies, stars, and cosmic structures whose light has had enough time to reach us since the beginning of the universe. However, it is important to note that the observable universe is limited by a horizon, and there may be much more beyond what we can currently perceive. The event horizon becomes a barrier, a border. This thing that's always in the distance that you can never reach. No matter how quickly you travel, you'll never be able to get to that thing. We know that black holes eat things and grow. So think about what it means to be inside of a black hole. You'd have this point of space, this region of space that you could never get to, and it's always receding from you, a horizon. But also think about what it then means for you right now on Earth. If you look out into space, there is a horizon very, very far out away, beyond which we cannot see, but we know there's something there, but we can never possibly see. And no matter what speeds we travel at, we would never be able to get to it. That's remarkably similar to what you would experience on the inside of a black hole. It turns out that the mathematics of the interior of a black hole is almost identical to the mathematics of the exterior of the black hole. This is actually what is going on mathematically, and it makes sense as well. Now you may wonder, how can such a bold notion hold any merit? Allow me to present to you the quantitative evidence that underpins this extraordinary hypothesis. It draws upon the pillars of observation, mathematics, and theoretical frameworks that push the boundaries of our comprehension. First, let us consider the relentless pull of gravity. Black holes, known for their intense gravitational forces, possess the power to bend space and time, warping the very fabric of reality. Remarkably, our universe exhibits similar characteristics. As we study the distribution of matter and the trajectories of celestial objects, we find patterns that align with the gravitational effects expected within the confines of a black hole. But the drama doesn't end there. The cosmic microwave background radiation, a remnant of the early universe, holds crucial clues. Its precise measurements reveal a peculiar temperature distribution, an echo of primordial events. And when we scrutinize this intricate tapestry, we find striking similarities to the behavior of matter near the event horizon of a black hole. Quantum mechanics, the realm of the infinitesimally small, also adds its voice to this symphony of speculation. At the tiniest scales, where particles pop in and out of existence, where uncertainty reigns supreme, we encounter hints of a deeper connection. The intricate dance of quantum fields hints at a hidden unity, linking the microscopic world to the cosmic tapestry of a black hole. Yet, let us not forget the enchanting realm of mathematics, the language of the cosmos. Elegant equations, born from the brilliant minds of theoretical physicists, unveil a captivating dance between general relativity and quantum mechanics. They whisper of an underlying harmony that could manifest itself in the black hole nature of our universe. This hypothesis challenges our conventional notions, shattering the boundaries of what we thought we knew. But if the universe were indeed a black hole, what could this mean for us? It would have profound implications for our understanding of reality and the human experience within it. One of these implications is that the idea of our universe being a black hole challenges traditional notions of the universe's origin. The Big Bang, its purpose, and fate. It prompts us to reconsider our place in the cosmos and raises profound existential questions. If the universe is a black hole, it invites contemplation about the nature of reality, the limits of our knowledge, and the ultimate destiny of the universe and everything within it. Also, the presence of a singularity, a point of infinite density, at the center of black holes raises questions about the laws of physics and the nature of reality. If the universe were a black hole, it could imply the existence of a central singularity affecting our entire cosmic framework. Exploring the interplay between general relativity and quantum mechanics within this context could uncover new insights and potentially revolutionize our understanding of fundamental physics. And finally, being within a black hole would mean that we are enclosed within an event horizon, a boundary beyond which nothing can escape. This confinement would fundamentally alter our perception of space, time, and our ability to explore the cosmos. The boundaries of our existence would be defined by the properties and limitations of black holes. The debate between whether our universe emerged from the Big Bang or exists within a black hole involves intriguing hypotheses and ongoing scientific inquiries. The Big Bang theory posits that the universe started from an immensely dense state and has been expanding ever since, supported by evidence like cosmic background radiation and the abundance of light elements. However, an alternative concept suggests our universe might exist within a black hole, questioning the Big Bang's singularity and proposing a different origin narrative. Critics of the Big Bang theory raise queries about its early moments, particularly the singularity and the conditions preceding the known laws of physics. Conversely, the idea of our universe existing within a black hole draws attention to possible parallels in gravitational behaviors, but faces challenges in reconciling observable phenomena with its framework. In conclusion, while the Big Bang theory remains the most widely accepted explanation for the universe's origin and evolution, ongoing research probes its early moments and seeks to address discrepancies. The concept of our universe existing within a black hole presents intriguing possibilities, but requires further evidence and refinement to challenge or complement the established understanding of cosmic origins. Scientific exploration continually evolves, aiming to unravel the mysteries surrounding the birth and nature of our universe. Alright, this is where I will end this video. Like, subscribe, share your thoughts down in the comments, and I'll see you in my next video.